Today we are going to talk about the Petrov-Galerkin finite element formulation for incompressible flow. There will be a series of videos on this topic. In fact, we can also extend this field of knowledge to a number of broader topics that related to this formulation. But for now, I only consider this series of video as a step-by-step guide to help you program Petrov-Galerkin finite element formulation for incompressible flow in the most practical way. As time goes on, I will definitely extend this to multiple topics stemmed from or related to finite element methods. So today, let us start talking about the governing equations of incompressible flow first. First of all, what we present here are the governing equations of incompressible flow. The first equation is called conservation of mass. For any fluid, the conservation of mass requires that the rate of change of mass inside a control volume equals the net flux of mass through its boundary. Before proceeding further, we need to clearly define what is an incompressible flow. Mathematically, the definition of incompressible flow says that a flow is incompressible if its velocity field is divergence-free. Observing from the general continuity equation, we can say that if a fluid's velocity field is divergence-free, its density's material derivative is also zero. In other words, for an incompressible flow, the density of its fluid particle will remain constant at all time. However, it is not necessary for density of fluid to be constant everywhere in the flow field. However, if the fluid density is indeed constant everywhere, this flow fluid is automatically divergence-free and incompressible. Hence, a constant fluid density is just a special case of incompressible flow. The second equation on top is the conservation of momentum, which is also called Navier-Stokes equation. In our case here, what we are presenting is its form for the incompressible flow, in which the fluid density is assumed to be constant. On the left-hand side of Navier-Stokes equation, we have a time variation term and an advection term, in which the advection term is common in all flowing matters as a product from Reynolds transport theorem. It is also very critical to the flow stability of the fluid flow in the sense that the advection term manifests itself as a bifurcation parameter, which has the capability to change the type of partial differential equation locally and globally. Here we are referring to the Navier-Stokes equation. If we look closer, we can see that the Navier-Stokes equation itself is originated from the basic Newton's second law, which says mass times acceleration equals to the force. You will also remember that the Newton's second law is documented in Lagrangian description. However, the fluid field is usually described in Eulerian description. With the help of Reynolds transport theorem, we can convert everything from the material derivative, which is the Lagrangian description, into the Eulerian description as shown here. Before discussing the finite element formulation, we assume that the fluid density is constant and divide every term in Navier-Stokes equation by the fluid density. In other words, you may imagine that we take the fluid density as unity. This is very helpful for numerical stability in scientific computation. Let us explain this further. For instance, the water is one of the most common fluid, which has a density of 1,000 kilograms per meter cubic. If we multiply every term in Navier-Stokes equation by 1,000 in the case of water, the difference of magnitude between the fluid density, which is 1,000, and the minimum number in computational field, which is usually 0.001, the common convergence error in finite element formulation, can be as large as 10 to the power of 6. This huge difference in the order of magnitude of numerical solution can tremendously increase the condition number of system matrices and possibly lead to the divergence of transient simulation. Now, if we got a chance to successfully formulate the variational form of incompressible flow once, you will realize that the finite element terms associated with the time derivative and advection terms are usually straightforward. Usually, the tricky parts in variational form are related to the force terms on the right-hand side of Navier-Stokes equation. For example, if you read a number of academic journal articles, you may realize that sometimes the gravitational term and/or the external force term disappears in Navier-Stokes equation. This is due to the careful considerations in each distinct case of fluid flow. For example, if we want to study the fluid flow of single-phase homogeneous and isotropic fluid medium, like water and seawater, it is advantageous to combine the gravitational and pressure terms together to form a modified pressure term. However, you will have to bear in mind that your gravitational effect is implicitly included in your modified pressure term, especially when the elevation of pressure measurement changes significantly. On the other hand, if we want to study the fluid dynamics of multi-phase flow or free surface effect, like ocean wave or stratified flow, it is a good idea to include the gravitational term explicitly in Navier-Stokes equation AMD, the associated finite element formulation. In other words, the decision is made case by case. It is also noteworthy that there is an obvious sign change of gravitational elevation, the symbol Z, in the derivation of the modified pressure term. If you recall how we calculate the hydrostatic pressure in fluid mechanics class, you can see that the positive direction of Z coordinate is pointing downward. This is usually conflict with our CFD simulation, in which we often take the upward direction as positive. Therefore, we will need to switch the sign of Z coordinate in the hydrostatic pressure term defined by the gravitational force. Now, we are almost ready for deriving the variational form of Navier-Stokes equation. Something we are still missing is related to the subtle numerical stability of our formulation. We all know that the conservation of mass or the continuity equation act as a way to ensure our flow is incompressible if we solve it together with Navier-Stokes equation. If we strongly couple it with Navier-Stokes equation in the system matrix and solve them all together using linear algebra, the unique solution is guaranteed to be incompressible, and the problem is closed. However, what about the numerical stability of this partial differential equation system? Especially, if we increase the Reynolds number into the turbulent regime, the system becomes super stiff, which means the previously stable numerical solution become very sensitive to the numerical errors and/or background noise, and may quickly goes into divergence in turbulent flow. To improve the numerical stability of the PDE system, it is advantageous to implicitly embed the incompressibility into Navier-Stokes equation, besides the strong coupling with the continuity equation. As a result, we also successfully reduce the terms in the stress tensor so as to distinguish it with the stress tensor incompressible flow. Now, let us dig deeper in this regard. We first write the incompressible Navier-Stokes equation into its component form in x, y, and z direction. Since we know the divergence of velocity field is 0, we take the partial derivative of continuity equation and substitute them into the component forms of Navier-Stokes equation. This should not change anything in numerical solution, but significantly improve the numerical stability of incompressible flow in turbulent flow regime. After substituting the continuity equation into the component forms of incompressible Navier-Stokes equation, we can do a little simplification and combine the similar terms as shown on this page. Following that, we try to write the component forms of Navier-Stokes equation into its matrix form. Here, you will realize that we can write the diffusion term into a very specific matrix form, which we call the Cauchy stress tensor, sigma. Finally, we have a clearly defined Cauchy stress tensor, sigma, which is consisted of pressure and diffusion terms, as shown below. Now, we are able to write the incompressible Navier-Stokes equation in a very succinct and robust form, which is not only numerically stable, but also mathematically correct. At this stage, we have prepared the correct forms of governing equations of incompressible flow for finite element formulation. In the next video, we will start working on the variational forms of incompressible Navier-Stokes equation.